this specific section that I'm looking at here is about compound probability and specifically looking at conditional probability. So you can kind of play with these different events. And so A would be an event, and then you have all these balls that are falling uniformly in space. And so if it falls over A, then you have an event that's in, or you have an outcome that's in event A. So in this case, you can see like what the probability of each event is. So you can move A around, you can move each of these around and kind of adjust everything. So here you can see all the probabilities for A, B, and C. And you can tell, I think this is the easier version of comparing independence and mutually exclusive, is that if two things are mutually exclusive, you know that there's no overlap. So as long as A and B don't overlap with each other, then they're mutually exclusive. And another way to know is if you want to take your conditional probability version by saying, okay, well, what if we knew that we had A? Well, then the probability of B becomes 0, because if we condition on A, B is not possible anymore. So that's another hint that you've got mutually exclusive events. So another example where we can see independence, using the definition of independence, where you have the conditional probability, you know that if you have a probability of A equals to 0.5, and that event is independent of B, then you could condition on B, and the probability of A is still 0.5. So whether you're in the entire universe of possibilities or whether you're conditioning on one of the independent events, so A and B here are independent, C you can just ignore, it's just kind of out here. I guess you can think of it as another event that's mutually exclusive from A or B. But if you condition on A, probability of B given A is 0.5. You condition on B, or let's just compare to the overall universe, right? You condition on A, probability B given A is 0.5. You look at the universe, probability B is still 0.5, whether or not you condition it. And the same thing for probability of A, whether or not you condition on B, it's still going to be 0.5. So 0.5 is used a lot here. So I made one other version that you can see where the numbers are different. The probability of A here is 0.5 and the probability of B is 0.1. So all that, if you have the events being independent, you just need the probabilities to not change when you condition on another event that's independent of that event. So here, probability of A is 0.5. If I condition on B, probability of A is still 0.5. Okay, and go back to the universe. If probability of B is 0.1, meaning like 1 out of 10 times the balls are going to hit B, but then I condition on A, then probability B given A is still 0.1, because in this reduced sample space, B still covers 1/10 of the area. And so 1/10 of these balls that are falling are going to fall in there. Okay, let me know if you have questions.